All right. Okay, so what we are going to do next, I think today is going to be like a very low key, like, like easygoing physics lecture, because the material that we are about to see is going to be kind of light in comparison to what we have done before. I think so. All right. And it's kind of fun because all you need is pretty much like algebra. Okay. So what we are about to do before we end this handout, we have like a tiny portion of this toward the end of this handout, which is about the speed of waves on strings. Okay. However, I sort of like discussed these particular topics many times and try to come up with like what you're seeing in the slide right now is like a verification or some sort of like the origin of this formula, and it somehow seems like the audience didn't like it so much in the past. So what I would like to sort of like have you guys take a look at is this expression right here. And that's it. Is that good? So instead of going through like, hey, you have to look at the free body diagram of the string and then take a look at the force acting on it, look at the motion, look at the acceleration or a centripetal force or other stuff, and then come up with the approximation. At the end, what you get is this expression right here. And that's it. It's done. All right, is that cool? I know it might not be so cool for some, but I think, see, for example, how so? So I think I would like to leave this like a hidden stuff for you guys to try. For those of you that are really keen to look at the way that it arrived at this expression, so this means I have those of you to look at this slide and try to come up with like how can we get to that. Sounds like a good plan. All right, for the rest of you guys, all right.
แล้วให้หอพาขึ้นไปสู่ความสดชื่นของเมืองไทยยังมีอีกหลายมุมในไทยรอให้เราออกไปสู่ลมหายใจออกเดินทางได้แล้ววันนี้สแกนเลย
Look at this one, it's very intuitive. Okay. Oh, you hear a commercial. What is that? Oh, my sound effects. Oh, all right. Yeah, I didn't pay for it, so that's what it is.
Okay.
Is it good? All right. All right. Thank you very much. All right. So what we have over here is, yeah, +1. Yeah, nobody paid for anything. Okay. So what we have over here is very intuitive, because if you look at the formula, this formula is about to explain to you how can you calculate the speed of wave. So don't forget, this is the wave speed. And I think you guys start to familiar with this because it's the speed of the propagation of disturbance. Okay. Don't forget, we have two speeds. All right. Or if you want to talk in terms of the direction, there are two velocities. One velocity or the speed is the wave, is the propagation of the wave. And the other one is just the oscillation of the medium. Okay. You guys got that from last time? Okay, so you have to make sure that you have two movements in one, and that created the animation, created the two variables function. It's created everything last time. But what we are looking at this point is just the speed of wave propagation of that disturbance right there. And now if you particularly look at the string, we want to know like, hey, how fast the wave will travel in a particular string. So what we did last time was purely math. It's a mathematical analysis. So it's a pure mathematics. But what we are doing right now is we make connection to the physical parameter. So how fast the waves will travel depends on two things. We discussed this briefly already last time qualitatively. So first of all, it depends on how high is the tension in the string. All right, remember we sort of like, we can relate this one to the string instruments. In the musical instruments, if you try to tune the string, and then for example guitar, and then you sort of like, you pull the knob or whatever, you turn the knob and make it a little bit more tighter and tighter, so the sound will have a different pitch. Okay, the frequency will change, and that is the indication that the speed of the wave in that string is already changed as well. Okay, sounds good. Even though we will need the connections between the speed and the frequency or the pitch later. That was later. But for now, at least you know that the tension in the string has an effect on the speed of wave. And you can kind of think about it like if you have a string and it's so tightly, together, you feel like a high tension in it. Every time that you put a disturbance on it, it should be able to propagate pretty quickly because you sort of like, you're on edge all the time. It's sort of like exciting. You're ready to propagate whatever things that hit you. And you just, so that's good. So at least the higher the T, the higher the V. So it looks good. Okay, but the square roots, too bad, it came from the derivation of the formula. All right, another one is look at the mu. The mu over here, it was defined as the mass per length. So we discussed this a couple of times already, that the mass per length, you can talk about this one as the density. All right, even though the regular definition of density is the mass per volume, but for the string, you can think of this one as a one-dimensional object. So when you have only one-dimensional object, you don't have the width, you don't have the depth, you only have the length. So mass per length is already qualified as a density. All right. So you can call this one as a density of the string. And sometimes people throw the adjective like the linear. So they might put this one as the linear density. So the linear term just to indicate that this is per unit length. You only have one dimension of the length. Okay, sounds good. All right, and now you can think, once again, we can go back to that, the instrument, the musical instruments there. When you look at the guitar, you have different, like the string itself have different thickness. So that is a different mass per length. If you have like a bass line over there, it's going to be pretty thick. And then when you go down to a thinner one, it has a higher pitch down there. So you can at least say the thicker string, it looks heavier per unit length. And that means you have a higher mu for a thicker one. But a thicker one, it seems like, okay, you think about it, if you want to move something with a high mass, it's going to be tough because it has a lot of inertia. So that's why with the mu, the bigger the mu, the slower the waves will travel. Does that make sense? All right. So at least the proportional things seems to be all right. Okay. However, the square root, this came from the derivation right here. All right. So that's what we do. We're just going to use this one and just understand that you need only two parameters to indicate or to determine the speed of the wave in the string. And that's it. It's done. Sounds like we can just pretty much mix and match this particular formula anytime that you really want to calculate the speed of waves given either the tension and the mass per unit length, or now you can extract the speed of waves through if you have a mathematical description. Sounds like a good plan. So I hope you see that sort of like the two ways that you can arrive to this. If you have a mathematical description, all right, you look at it, sine, cosine, x minus vt, x plus vt, everything, and you extract the information from the mathematical expressions. Or on the other hand, you might look physical. So you look into some physical stuff, and the physical parameters that you need is only the tension and the mass per unit length. And that will allow you to calculate the speed of waves already. Okay, so I hope you see like a parallel sort of like ways that you can arrive to how fast the waves will move. Okay, so that's a question comes in. What if the medium is water like ocean? Yeah, that's different. So if you have different system, you will need system formula. Okay, so of course you won't have any tension in the water. That's kind of bad, but there will be a way that you can describe that. Yeah, all right. But even though I don't think we're going to cover it in the, maybe in the physics textbook, they might talk about that. Yeah, that's kind of in it. Okay, so just for those of you that sort of are interested in, so in the liquid type like water, instead of having a tension, you need some parameter that tells you the elasticity ability for that to pretty much like change the shape and all this stuff. So for that, it will link to some sort of like when you talk about elastic modulus. Sounds good. I don't know. You probably learned about Young modulus before. Okay, so that's the modulus that you're going to use for the liquid. And then you divide that by the density, the actual density. So it will look something like, so just on passing, it might look like something like some modulus on that liquid divided by the rho. All right, but the factor or the form of the equation looks very similar for that type. That's a good question though. Yeah, but I mean, we don't want to make things too complicated, so we just stick with the string, the one-dimensional system. Sounds good? All righty. Okay, so let's take a look at some examples right here and then just give you a sense of what is going on, and this will give you like a pretty much like summary of the things that you have already done last week. Take a look at this. Suppose you create a pulse by moving a free ends of a taut string up and down once with your hand, beginning at time 0. All right, so you pretty much like, you might have a string attached to the wall, and you have string right here, and then your hand is right there, that ugly hand there. And then you move your hand ups and down just to create a pulse, just one pulse. Okay, the pulse reaches the wall at time t. So this one at time 0, and of course the pulse will travel and it hits the wall at time t, which is t equal to t. That's kind of weird. All right, but that's the t on the left is your variable. Which of the following actions decreases the time? So which of these actions will make waves travel faster? All right, guys, go through these choices and take a look. What's your answer? Whew. You don't need that. That's kind of annoying. I still don't have another kind of music here. It's still this app right here. Okay, guys, go through this. A, moving your hand more quickly. Would that help? B, moving your hands at greater distance up and down. So you go up and down further. C, using heavier string. So you change the string, make it a thicker one. I mean, a heavier one. All right, but keep the length and the tension the same. And D, using a string the same linear mass density. So that means you're still using the same thickness of the string, but you reduce the tension a bit. All right, guys. So you want wave to travel faster. What can you do? Oh, C. All right. With the question mark. Okay, very good. Still like unsure a little bit. All right. So if you use a heavier string, so we saw from last time is actually it's counter the speed of waves though. The heavier the string, the slower the wave will travel. So actually that's not good. C is not good. All right. You want it to move faster because you want to reduce the time T. Yeah, you're right. A then, all right, moving your hand more quickly. So if you move your hand up and down quickly, what you do to the pulse, you're just going to change the shape of the pulse. If you move your hand quickly, so it means you go up and down faster, the pulse will just be thinner, up and down. So your pulse will be narrower. But that won't change anything though, right? Because you won't change the tension. You didn't change the linear mass density. Oh, D then, all right. Using the string of the same linear, but then decrease the tension. Then you look at this one, you can see that the tension, if you want to get things move faster, you're supposed to increase, not decrease. So actually, D is not good. So now we have left with just the B, moving the hand at a greater distance. If you move hand greater distance, what you're getting, you're just going to get a higher waves pulse. So the answer is not bad. They're all bad. No, none of this. So this is not a multiple choice.
Okay, I have an answer again.
The what?
My answer is make the string the radius, reduce the radius of the string.
Okay, that can do, yeah. At least, yeah, that is true. When you reduce the radius, then you make the string lighter. That will be fine. But the key is the mass per length. So you have to change the density, not just the shape of the string. Yeah, so there were no choices in the beginning. So the question is bad. Which of the followings? The answer is none. No, nothing. None of this works. All right. Well, it's just which of the following. So it could be more than one or it could be zero, right? Why you do this? Sorry. Sorry, my bad, my bad. I didn't mean to. All right, it was just accidentally. Pain. Sorry. All right, keep going. All right, this one is more serious now. All right, so this one is more like a physics-ish, type of question. All right, guys, try this and see if you can crack this one. I hope you can. Right? It's not that bad, even though you might be seeing this for the first time, but it needs a little bit of understanding of how things go to incorporate the waves calculation into this type of question. So you have a light string with a mass per unit length of 8 grams per meter. So when you have this given, so you already see that you get the information about the mu. The mu is right there, even though the units is kind of bad, but it's a mu anyway. All right. So has its ends tied to two walls separated by a distance equal to the 3/4. All right. So that's given in the figure already nicely, 3/4 of the length between the walls. An object of mass M is suspended from the center of the string. All right, cool. Putting the tension in the string, that's fine. So everything is going to sort of like get pushed down a little bit. So find the expression of the transverse wave speed. So what they want you to figure out is the wave speed. Even though it's called transverse, we know the transverse, just the wave that is going to get created in a string is going to be a transverse wave. That's all. All right. So even though they don't put the transverse wave, you guys understand that this kind of wave is going to be a transverse type. So you try to figure out the speed of the wave in the string as a function of mass of the hanging objects. All right. So if you can get part A, part B is just plugging in the number. So actually the main question of this problem is just part A. All right, guys, go ahead. Ooh. Give it a shot. All right, you have to imagine first what is about to happen. Okay, so you put a mass just so this will create a tension in the string. And you want to create a wave that travel along this string. So it's feel like when you're hanging the mass, you pull the string down, it creates a tension on here, and then you can like pluck the string a little bit. So you generate a wave, and the wave will travel along this string. That's what it means. Sounds good? All right, and you want to figure out how fast the wave will travel in this string right here. All right, cool. All right, for those of you that sort of get stuck a little bit, don't worry, because we only have one thing to calculate, is this. That's it. All you need is just a tension in the string and the mass per unit length. The good thing is the mass per unit length is already given. That's the information is already given in the problems. So the only thing left for you to calculate is the tension. So now your question go back to mechanics, right? So what is the tension in the string? So go ahead. So we do free body diagram. When you do free body, now you want the tension. So I would like to pay attention to that joint right there. Okay, so I'm just going to focus on that joint and try to see what are the forces acting on that point at the joint. Sounds good? All right, so you think of it like a free body, the string at the point of the hanging positions right there on the string, something like that. So with that, then you say, okay, John, no problem. Mg is down. There will be tension along the string. Tension along the string. Because of the symmetry of this, the tension on the string is supposed to be exactly the same. Because you know exactly if you break this into two components, yeah, break this and break that. Okay, everyone with me so far? All right, so you guys know that the horizontal components are supposed to cancel each other out, and that's guarantee the magnitude of the tensions supposed to be the same on both sides of the string. Okay, cool. All right. So with that, then all you need further is now, what about the angle? So you can define an angle right there. If you call that theta, this will be theta as well. Okay, good. So far, so good. All right. And then with that theta, I can extend this one out a little bit. This is also theta. It looks dirty, but I hope it works. All right. So what you get that pointing upward is going to be t cosine theta. Two of them. You guys follow? Okay, so the component that pointing up is right there. That's t cosine theta. That component right there is another t cosine theta. Okay, and that's it. It's almost done. So with that, what you have is the 2 of the t cosine theta pointing up is going to be equal to the mg that's pointing down. Okay, the theta is not too bad because if you want to figure out the theta, you have this right triangle over here. I pull it out just to make it a little bit cleaner. It's 3L/8. Okay, so that triangle that you are looking at is going to be 3/8 of the L and the hypotenuse of L/2. So from this information, you'll be able to figure out the cosine theta already, which, I mean, the number is going to be bad. All right, this is like a dot, dot, dot over here. You guys do Pythagorean theorem for me. Right. All right, but the point is you get the tension. So over here, tension is going to be mg/2 cosine theta, which are known. All right, conclusion is your final answer will be the speed is going to be square root t over mu, and that is just going to be square root mg/2 mu cosine theta. And that's it. Just leave it there. All right. G is known. Mu is known. Cosine theta, the theta is known. So this is already speed of the traveling wave as a function of mass. Done. Woo. All right. Part B, you can just plug in the numbers. If you want the speed to be 60 meters per second, you can figure out what is the weight of the mass or the mass of the mass that you have to put to hang on this string to generate 60 meters per second wave speed. Sounds good? All right, so I think this is easy enough. And just so you can see that the kind of question that will show up in the exam is going to be about this. It's not going to be too complicated, at least just for you to have a chance to try out this particular expression, square root t over mu. Sounds good? And that's it. All right, it's considered done for this handouts right here. So any questions so far? All right, so I think you guys already equipped with, wow, mathematical description of sinusoidal waves or any type of waves. You know the characteristic of that is supposed to be two variable functions. And now you have some connections, some physical connections to the wave in a string. Square root t over mu will give you the speed. Okay, pretty good. All right, that's a good setup there. All right, keep that in mind. We'll have a chance to come back from time to time. From time to time, it's like, because the next topic that we're about to cover, we're gonna sort of jump away from this and look at something a little bit sort of simpler, I hope. All right, so what we are, oh, where does this one go? Jump right into the end. Okay, so we are going to look at one particular type of waves, and it's sounds. Sound wave. Okay, so we're going to have some aspect of sound waves that we would like to cover, and it will generate something that's sort of like relatable to your everyday lives. I think that's kind of cool. And what we are trying to cover today, I think that's my plan. I will try to get you to talk about the sound wave a little bit with connections with what we did last week. And we try to calculate its intensity. And we're going to define what does it mean by the intensity of sound. All right. And I would like to, if time is good, end today's lecture with Doppler effect, which is like so cool. All right. I think we use this a lot. All right. And we're going to leave the interference of sounds, or actually it's an interference of waves, next time. Okay. Sounds like a good plan. All right. Let's jump right into it. Okay. So I think you guys know this a little bit already. That the sound waves is a longitudinal waves. Okay, because the way that you generate a sound, it looks like this, right? Even though this one is called tuning fork. Tuning fork is just I had it before, I lost it, I suppose, but it's just like a simple metal bar. And when you sort of like make it sort of like you can hit on it, make it vibrate, that vibration will generate sound. Okay. And that's how simple it is to generate sound. It's the same thing as a diaphragm in your speaker. It's the same thing as a diaphragm in your vocal cord and everything. So everything has to move back and forth, back and forth. And that back and forth movements will push and pull the air around it, and it generate the compression and decompression of the air. And that compression and decompression will spread out in terms of sound. So this is the reason why if you're looking at the molecule of the air is going to oscillate back and forth, in this case, in the horizontal direction, which is the same direction as the propagation of that disturbance. Sounds good? All right. So this is no question why sound is a longitudinal waves. Okay. But then the thing is, if you read the textbook, there will be like an earlier part of this text that talk about the waves can be described in two ways. We probably familiar with this. It's just the movement of the air itself. But everyone knows from thermodynamics, we don't want to deal with the molecules, right? That's too complicated. We have to express them in terms of some parameter that can be measured in the macroscopic level, such as the pressure. All right, we know, right? When you talk about the air, I mean, the gas, we can measure pressure. So instead of talking about the movement of the molecule, you might want to talk about the pressure change. The portion where the molecule of the air are closer together, that's going to represent a higher pressure area. And the area that the air molecules are further apart, that will be the part where the pressure is low. So if you look into that, then the pressure change will have the wave pattern as well. And that is the second curve right here. All right. And once again, you have to call it as the pressure change because you have to compare the change with respect to the regular pressure. Okay. But no matter what, all right, the complication that you might find in the textbook is they try to come up with the description of that pressure change. And they're going to discuss about the phase difference because you can see that the form of the waves looks like it's the blue, and you shift the blue to the right a little bit. So if we talk personally right now, we just talk personally. All right, we don't want to deal with this too much because, yeah, I have to introduce to you how can you calculate the pressure. And I mean, if we talk about the form of the wave, and this one just to remind you what it means by telling you the position on the wave, you can see that these two waves, the blue and the orange, has the phase difference, okay, with me, equal to pi over 2. If I write it like this, you guys okay with me? This is like testing the water a little bit. Okay, here. The peak of the blue waves is right at 0, 0. But look at the orange waves is down to 0 already. Or you can think of it like the peak already moved forward a little bit. But a little bit is 1/4 of the whole cycle. You can see that the whole cycle is right here. That's one cycle. So that means if you chop this into 4 parts, each part will contribute pi over 2, pi over 2, pi over 2, pi over 2. Phase difference. Okay, you guys with me, yeah? All right, so when you can see that the separation between these two dots is only 1/4 of a cycle. So you can tell that the phase difference between these two waves is 90 degrees or pi over 2. All right.
Okay.
All right, keep that in mind. So we're going to have a chance to come back and talk about the phase, the positions of waves, and what happens when they meet. And that will be next week, next lecture, sorry. Yeah, sounds good. All right, but for now, that's okay. We don't want to talk too much about the pressure waves, but at least just so you know that no matter you are looking at the displacement of the air molecule, or if you look at the pressure change, they will have a sinusoidal pattern anyway. So the mathematics that we learned last week still work, okay? And it's still simple harmonic and all this stuff. Okay, all right. Now, but we're gonna move away from that. As I promised, today is gonna be simple. It's gonna be purely algebra. So we would like to turn our attention to the aspect of energy. All right. And to talk about the energy, the common way that they can describe how much energy that the waves carry along with it is through the intensity. So even though we are learning intensity of sound, but actually this intensity definition works with any waves. You can talk about the intensity of light. You can talk about the intensity of water's wave. You can talk about the intensity of this and that. But the reason for sound is if you're looking at a point source, and this is kind of hard to generate in other types of waves. If you have a point source, so that means it's a source that can generate the disturbance of the waves in all directions. I wouldn't say even 360. It has to be like 720. It might not even work. You might have to speak about the solid angle and stuff. But it's the point source that generate waves in every direction around you. Okay. So that means the wave fronts, the front of the wave that propagated out from that point source will have a shape of a sphere. You guys with me? All right. So you can think of it like you generate a wave that go out in all direction and moving out in a spherical manner. Okay. The good thing about this one is it's look very highly symmetric. It's hard for you to generate a point source in other types of waves. Light possible, I think, but I mean, for the mechanical system, sound is the best. Okay, so that's why we're focusing on sound. Okay, now if you have an information about the power that emitted from this point source, and you guys remember the concept of, I mean, not the concept, the definition of power. The power is just the energy per unit time. Yes. Okay, so you can think of it like a delivery of the energy or the flow of energy or the rate of transferring of the energy, whatever, per unit time. So that is the power. So if you are given this information, it turns out that the intensity at particular point is simply defined as the ratio between the power per unit area. Done. That's it, guys. You will find that today's lecture is like, it's purely like definitions. All right. So the concept of the intensity is simple. Calculate the power, energy per unit time, and divided by the area that this whole power is sort of like cover. Okay. So in this point source thing, that's easy to do. The reason I say it's easy to do is because you know that the area of a spherical surface is 4 pi r squared. Depends on the distance. Okay, so that's good. So you take the power from the source divided by 4 pi r squared, and then you're done. And this is the reason why you can see that I is proportional to 1 over r squared. And this is the reason why when you running, you don't have to run, when you move away from a speaker or whoever talking, then the sound that you hear is going to get more quiet. More quiet, quieter. All right. I mean, okay. The sound will get quieter. Is that the word? Quieter? Okay. Okay. All right. Anyway, it's harder to hear because it's inversely proportional to the distance square. So that gives you some sort of like a clue that actually the sound level, okay, the loudness of the sound that you hear in your ear depends on the intensity. The higher the intensity, that means the sound is loud. Okay, the lower the intensity, that's kind of quiet. All right, cool. So this is the reason why we define this, because we know that it interacts with human this way through the intensity. All right. So that's what it is. Now, give it a shot. So if you have a fireworks rockets explodes at a height of 100 meters above the ground. All right. So let me draw some diagram here. So there's a rocket explode, bam, something here. All right. And it's 100 meters above. So let me put a scale here right there. Now, an observer on the ground directly underneath that explosion experiences an average sound intensity. All right, so there's a guy here underneath, and he hear the sound with the intensity of 7 times 10 to the 2, or negative 2, sorry, watt per square meter. You look at the units, guys. Is it good?
Okay.
Yeah, unit is watt. Watt is power. Area is meters square. So that's good. That is the unit of intensity. All right. And we can assume that this explosion generates sound wave in all directions. So that means we assume that this explosion is a point source. So it means you generate sounds sort of like in all direction like this. Okay, cool. All right. Now it turns out he's experienced this for the interval of time of 0.2 seconds. Some of you might prefer delta t, but that's fine. All right, I think you guys know what it means. It's 3D. Yeah, it's in all direction in three-dimensional space. Yeah, all directions. Okay, so what is the total sound energy of the explosion? So this is not bad to do, because what you can see is the intensity is the power per unit area. And because we treat this to be a point source, the area that we are talking about is 4 pi r squared. And the order we're talking about right here is exactly 100 meters, because that is from the center of the explosion to this dude right here. That's 100 meters. So that is already R. Cool. All right. So that's nice. But what they want is not the power. They want to figure out the energy, which is fine. We know further that the power over here can be written as the energy from the source per time interval. All right, you can put delta t or t if you like. So from that, I can write E to be I, intensity, times 4 pi r squared times the delta t. You guys with me? I just move everything to the other side and leave the E, just like a final answer that we would like to calculate. All right, and the rest, all you need to do is just plug in the number. Intensity is known. Okay, 4 pi r squared is easy. The distance is already in meter. That's nice. Delta t is already in second. That's it, guys. The answer that you get will be in joules. And you're done. Already. All right, easy enough. Sounds good. But at least that gives you an idea of what we are about to do right now. Okay. All right. So far, so good. All right. Try again. So the area of typical eardrum, so this is, you can imagine your own eardrum, is about 5 times 10 to the negative 5 square meter. Calculate the sound power incident on an eardrum at the threshold of hearing. So now I'm introducing to you some numbers right here. It turns out that humans start hearing things at about, on average, 10 to the negative 12 watts per square meter. Okay, so that's sort of like average for the whole population of this earth and all this stuff. All right, so what will be the power on the eardrum? So that's good. So part A is straightforward, because this one you already known the I. Let me call I naught over here, but that's the threshold. So what you have is I is just a power per unit area. But now, because we are not talking about the point source anymore, okay, so this particular problem just want to show you that the definition of the intensity is straightforward. It's a power per unit area. So if you are looking at the problem that doesn't talk about the point source, or you don't assume that there is a point source here, you just take the power divided by the area that you have. That's it. So over here, you can calculate the power to be just the intensity times the area that the sound is falling upon. And that is 5 I'm sorry, 10 to the negative 12. That's the intensity. Multiply by the area. It's already in square meter. Perfect. Then there you go. All right. Unit cancel definitely. You're going to get down to the watt as a final answer. And that is 5 times 10 to the negative 17. That is super small. All right. But actually, you don't need a lot of energy, right? It's right. So we talk about like watt. It's like 1 watt. That's going to blow your eardrums away. It's like very small part of your body, right? Okay, and part B, you do the same thing, but now you turn this to be like a threshold of pain. So let me call this, let me use different color here. Let me call this like subscript PI, then is I sub P over here. It's the threshold of pain, but you still use the same thing. Okay, the same definition, power per unit area. So the power that you start to feel pain in your ear is going to be 1 watt per square meter times the same surface area. And that's it. It's 5 times 10 to the negative 5 watts. All right. That's give you the range of your working ear or eardrum. All right. You're not supposed to receive too much of the power to your ear. That's not good. All right. Keep that in mind. Okay. This is done for the intensity. It's just showing you definition right here. Now, what that we really use is not the intensity though. Even though when you buy like a speaker system or whatever speaker, you have the rating of that speaker. If you notice, like you want to buy a speaker and this speaker is like 3,000 watts or 2,000 watts or 500 watts. That is the power from the speaker. And then you use that power, you can start by calculate the intensity that hits your ear on and on, but it turns out that still does not translate to what you are hearing anyway. I don't know, it's like sounds like confusing or not. But the thing is this. Think about it. If you are talking to your friend, okay, and one of your friends is sort of telling you the story or whatever, and suddenly, if you imagine that you have 10 of your friends speaking to you all at the same time, or you can imagine like in the classroom, for example, if one person is talking at this point in one moment in time, but then suddenly the whole class is speaking all together, I mean, at the same time, you do not hear the sound that much louder. Does that sound like something relatable? For example, if one person speak to you, all right, this much sound loudness, but then if you have tens of your friends talking at the same time, you don't hear the sound 10 times higher in terms of the loudness level. And the best sort of like example probably in the concerts. You're going to a concert, let's say you have 10,000 people screaming at the same time. You are not hearing 10,000 times louder sound. So that means there's a clue talking about, I mean, trying to tell that your ear does not respond to the amount or the numbers of sources in a linear fashion. Does that sound like a good explanation?
Okay.
Yeah, so this is like, okay, it doesn't seem to go linearly. So things going 10 times, the sound that you were listening to is not 10 times louder. Go to a concert, it's like 10,000 times. You have sources that multiply 10,000 times. You are not hearing the sound 10,000 times louder. And that leads you to the next parameter that you can use. It's called intensity level. So we would like to emphasize on the word level. It's right there. Level. Okay. So we won't get confused with the word intensity because this one is an intensity level. So the thing is, it turns out because we have non-linearity in our ear, what kind of things that will jump in and then help you with that? It turns out the logarithmic scale is very perfect because when you have one log of 1 is 0. When you have 10, log of 10 is 1. When you have 100, log 100 is 2. When you have 1,000, you get 3. When you have 10,000, that's 4. Do you see the property of log over here? So the logarithm is just the inverse function of the exponential. So what you're trying to do with the log is just to turn something that's grow exponentially back into a linear scale. 1, 2, 3, 4, 5, see? And that's it. That's what you want. So you want to turn something down from the exponential to a linear scale. You use the logarithmic function. Okay. Plus, you would like to create some parameter that can communicate with other people. So this is what they do. So you just take the intensity of whatever you are looking at. Then you take the ratio. You just want to know the relative intensity relative to, remember this one, the I naught that we introduced over here, that is the threshold of hearing. And we agree to use this number. That's what we agree, like globally, agree to this number. So you take the intensity that you want to calculate, the level, divided by 10 to the negative 12, and then you take a log, you will get the intensity level. All right. And the unit of this log over here is the bell. That's a B. And because you want to refine the scale a little bit to make it a little bit sort of higher resolution, so you multiplied it by 10, divided by 10. You leave 10 to this. And remember this, 10 divided by the bell, it's going to be 10 to the negative 1 bell. 10 to the negative 1 is deci. So that's why you get a decibel right here. Okay, so in conclusion, what you have here is a formula. Even though it looks like a formula, but it's nothing more than just, to me, a unit conversion. But it's a complicated conversion. It's a unit conversion that you want to convert the intensity, the I, into a decibel, which is the intensity level. And from now on, I think we're just going to call it level, just to make it clear. Okay, so you want to convert the intensity, watts per square meter, into level, decibels, through this relationship right here. It's a unit conversion. All right, so what you can try very simply is, if you look at when you have beta naught to be the threshold level, why not? Yeah, when you start hearing things, 10 log, you put I naught in the position of I, divided by I naught itself, that is 1. Log 1 is 0. So that's it. So the 0 decibel, that means you will start hearing sounds. Cool? All right. Why bells? I think it's Alexander Graham Bell, the one who created telephone, I think. So just to honor him, so we have this unit to honor the scientist who, created the first telephone or whatever, something like that. I don't know why. Just like why is Joules, why Newton. I think the unit just to honor those who invented this understanding and all this stuff for human. Okay. Yeah, I think that's a good question though. Yeah. I think internationally agree. Yeah. Okay. All right. So what we have over here is 0 decibel is the threshold of hearing. And then you can scale up. And as you can see, because we are dealing with the log scale, so every time that you go up 10 times, under the log, you're going 1. 100 times, you're going 2. 1,000 times, you're going 3. But then you have factor of 10 in the front. So there's no doubt to jump from 0 to 10 decibel, that means the source has 10 times more intensity. You guys with me? Okay, it's 1 order of magnitude higher. And then when you go up here, you see that it's now going to 30 decibel. So that means it's an indication that actually the source is already 1,000 times more intensity. Yeah, with me? Get the sense of this one. All right. So in conclusion, the decibel is the nonlinear scale, right? With the log scale, of course, built into it. And for those of you that doing computer science people, you use this unit with the noise as well, because the noise level is so low, right? And every time when you deal with something so low, and then when things jump up like 3 orders of magnitude, 5 orders of magnitudes, you cannot deal with the original noise level in a pure numbers. You take log over it. So that's why usually when you talk about the noise level, they come in a decibel as well, or even, you know, it's even though it doesn't have any things related to sound anymore, but it's the same formula. So that's why noise level sometimes come in the decibel units. Okay, all right, but at least you know it's nothing more than just a unit conversion. Okay, and you convert not only just your units, now you convert the scale from the linear and the exponential, the logarithmic scale. Okay, all right, let's practice a little bit and then we'll take a break. Sounds good? All right, so two identical machines are positioned the same distance from a worker. So the intensity of sound delivered by each machine at the location of the worker is given. Find the sound level heard by the worker if one machine is operating. Okay, one machine is operating is good. That's easy to do because you have a machine running. Okay. I don't even know what I'm drawing. It's supposed to be a machine. All right. Anyway, all right, this is like, okay, machine. Okay. And then you're standing right here. Sorry. All right. At some distance. Okay, you don't know. Okay, the intensity is delivered to this guy is 2 times 10 to the negative 7. So all you need to do is just convert, turn the intensity into intensity level. So go ahead. Beta, let me call beta 1, that's for one machine. It's going to be 10 log the intensity that this guy received. It's going to be 2 times 10 to the negative 7 divided by threshold of hearing intensity, 10 times the negative 12. Units cancel, which is good. It has to be. That's behind the log. Okay, and that's it. So what you have is 10 log 2 times 10 to the 5th. All right, and you can, I mean, if you have calculator, you can just punch the calculator. But for those of you that still want to do like some analytical way, I can write it like this. It's going to be log 2, just to sort of remind you, having fun with the math a little bit here. So log of a product is the sum of the log. So you can split the 2 times 10 to the 5th into log of 2 plus log of 10 to the 5th. All right, and this log of 10 to the 5th is nothing more than just number 5. So at the end, what you get over here is just going to be 10 log 2 plus 5. Or let me write it like this. So it's going to be here 50 plus 10 log 2. Sounds good? Okay?
Okay.
All right. But I just want to leave it there. I want to do part B. Part B, they say they just double this machine. So you have 2 machines running at the same time. So the new level is going to be 10 log. Now you only double the intensity. You guys with me now? Because the intensity related to the power related to the energy. So when you double the machines, you double the amount of energy delivered to you, you double the power. So that's why you have 4 times 10 to the negative 7 to be the source intensity now, twice the single machine. Still divided by the threshold of hearing. All right, so same math, except you change the number 2 to number 4. So at the end, what you're getting is going to be 10 log 4. So you start to see now what is going on here. So you double the source power, your hearing only changed a bit. It's 50 something to 50 something. Okay, if you take log 2 to be what? Log 2 is what? let's say approximately 0.3. So log 4 is going to be 2 log 2. So you only change by a bit. Okay, so this is a reason why, even though there's 5 machines running, it's going to be louder, but it's not going to be 5 times louder. It's going to be louder by this much. So in conclusion, the intensity levels is created just to reflect the non-linearity of your human response to the sound. That's all. Sounds good?
Okay.
Okay, so so let's stop here. Sounds good? I mean, not stop yet. Just take a break right here. And then for those of you that want to play around with it, look at these examples right here, and then I will show you how it's done after the breaks. Okay, sounds like a good plan? Okay. Okay. So, I don't know, have anyone tried this? Maybe not, I guess. Okay. All right. So, the sound level at a distance of 3 meters from a source is at 20 decibel. At what distance will the sound level be 100? All right. At least you know it. I mean, you have to stay further away from the source, but how far? Okay. So I would like to introduce, not introduce, but it's just like the way that I would like to approach this one, because it's like you have 2 scenarios, 2 situations, 2 states, 2 positions or whatever. So what usually I will do is just try to write out the expression for both scenario. So I can call the first scenario, which is at 3 meter, to be like subscript 1. So that means the sound level at this, I will call it beta 1. Oh, that's the wrong place. So let's call this beta 1. All right. And the new position, I will use a subscript 2 for that. Okay. So what I can do is I can just write beta 1 is going to be 10 log intensity at the position number 1 divided by threshold of hearing. And I do the same thing for the second position. It's going to be 10 log I2 over I0. And now the rest is just how would you like to manipulate this. Back in the day of thermodynamics, you have like PV equal to nRT. And because you want to compare between 1 and 2, what you got before was like P1 V1 over T1 equal to P2 V2 over T2. That one, just think of it like you take 2 equations and then you just divide them. And then you just get rid of the constants, and then you just manipulate the form to make it looks like this. Okay. But here you have logarithmic function right here. Divisions between 2 logs are not good, because you haven't seen like log A over log B, and not much you can manipulate from this. Even though some of you might remember, but Ajahn, you can do like log A with the base B, but that makes things even more complicated for us at this point. Okay, so what you would like to utilize here is the property of log that you have. If you have 2 log, in addition, you have the product between the arguments. We did this before. And you use the subtraction, the difference between 2 logs, you take the argument, and then you would have a ratio between them. Okay, this one looks good. The reason the last one looks good, because if you want to compare in the same light as you did with the PV equal to nRT, that's what you need in here. You want something to be in the ratio format, but that ratio is too bad. It has to happen after the log. So this gives you a clue that the way that you want to manipulate 2 logs is through the subtractions. Sounds like a good plan?
Okay.
Okay. All right. So if you guys agree with this, then what I'm going to do next is just, I'm going to take beta 1 minus beta 2. Or you can take beta 2 minus beta 1, but because I already have, I already see it, that the beta 1 is larger than beta 2, so I don't want to deal with the negative numbers, even though it's not that bad. All right, so it's going to be 120 minus 100. That's on the left side. And on the right side, what you have is going to be 10 log I1 over I0. Subtract out with this 10 log of I2 over I0. All right, I can pull out the common factor, the 10. And now you have 2 log. Doing the subtraction, you can pull them into one and take the ratio. You guys still follow so far? All right. So the difference of two logs, I just take the argument and then do the division. And of course, the I0 will disappear. So you only have left with just the I1 over I2. Is it good? All right.
Okay.
So the reason I want this, because of what? Now I want to bring you back to the definition of the I itself. The I, if I say I1, is going to link you to the power of the first source divided by 4 pi R1 square, given that assuming, because they don't give you any clue about the source. So you assume the point source to be the case here. All right. So you have everything related to the first case to be subscript with 1. And then same thing with the I2, you're going to link to the power of the second source, pi R2 square, the second distance right there. And because now you're dealing with the ratio, that allow you to go further deep into the power relationship between them to be P1 over 4 pi R1 square. And then I flip it over for the subscript 2. You guys with me so far? Yes? And that allow you to do the ratio between the first and the second scenarios here. Whatever cancel, 4 pi disappear. And because for this particular problem, you are not changing the source. So that means the P1 and P2 are exactly the same. So that means you can also cancel P1 and P2. But I mean, just in case for other problems that you want to like switch or change the source, the new source is that much higher than the first one, then you have the whatever, like maybe P2 is 3 times P1, on and on. So you can use this approach to take care of that case as well. Okay, sounds good? All right, but for us, in this case, you only change the distance. So that's already there. Now, you already seen that the R1 is right here, 3 meters. So that means you know the number right here already, R1 to be what? So the only thing left as an unknown to you is just R2. And that can be solved. So let's do that a little bit here. So in conclusion, you arrive at this. This left-hand side give you 20. 20 will cancel with the 10. You get on the left side to be 2 equal to log. Okay, and it's going to be R2 square over R1 square, which is 3 square right there. Now you can punch the calculator now if you like. And then for those of you that still like analytical approach, you can manipulate this one a little bit further, because log, when you do the inverse, it's just power base 10. So it's going to be 10 square is R2 over 3, the whole thing square. And that means R2 over 3 is just 10. And that means the new distance is 30 meters. There you go. And that is done. Okay. So as you can see, for you to reduce the level from 120 down to 100 decibel, you have to go far away, like 10 times. You have to go pretty far. Yeah, but I mean, you also know in your head now that changing of 20 decibel, that's a lot of change. That's 2 order of magnitude change in terms of the intensity. So there's no doubt you have to go pretty far. Okay, looks good already. All right, very nice. So I hope you pretty much get what this is about. It's about trying to look into the waves just from the perspective of the energy, or the energy delivery, which is in the unit, in the form of the power, energy per unit time. But then you want to, describe that even further, because waves might be incident on some surfaces. Then you take those energy delivery power per unit area that allow you to define intensity. But then you make connections to human hearing. So that's why you create another unit called decibel. And that the relationship of 10 log I over I naught, that is just a unit conversion, going from intensity to the decibel, intensity to the intensity level. So from watts per square meter to decibels. Okay, sounds like a good conclusion over here.
Okay.
That's nice. Okay, all right. So before we move on, Well, I don't know, is that a good news or bad news? All right. Before we move on here, I have another comments on this one that I didn't make comments before. There is the word, where did it go? Where did it go? Oh. I'm looking for the word average. I thought I saw it a couple of places. Okay. Yeah, okay, here we go. Found it here. So every time that you talk about this, you might see this one like very often, like average sound intensity. Even the formula itself, if you look carefully, some of you might just like sort of, Adan, why didn't you comment about this subscript right here? There's an AV down here, there's an average. So the reason for this is because now look back at the mathematical description of this. Everyone knows wave has an up and down, it's always moving, it's an animation. So that means to look at the wave at one particular time, that doesn't seem right. So you know what I'm saying? Because if you want to like freeze the time, just like what we did last week, I mean, the medium, the particle in the medium was just like standing at some point, but then so what? All right. So in general, if you would like to look at the wave as a total entity or something that you would like to describe, usually you have to let it move a little bit. So you have to go through some of those fluctuation or oscillations, and then you come up with an average value. So there's no doubt every time you talk about waves, there's always a word of average, because at the minimum, you should allow the wave to complete its one cycle. Does that make sense to you?
Okay.
Yeah. So no, don't worry about the words average too much about the waves topic, because they have to do that. If they only know this wave half of the way, that would be bad, because you don't even sure like, hey, is this going to be like a real complete periodic wave, or is it just a pulse? So just to be sure, you just have to let it go for a while until you can see, oh, there's a pattern right here. And this pattern seems to be stable. And then you come up with an average value, something like this. All right. So that's just my comments on the word average. It has to be here at all time. Okay. Okay. So you don't have to get too confused about this. All right. So the reason that I mentioned about good news or bad news, there is a double effect I want to get into next, but I don't think time is enough. I have to end this lecture a little bit early because I have to have an appointment at exactly at 12, and I cannot. I'm sorry, this is like suddenly happens just last night, so I might have to end the lecture a little bit earlier. Sorry, guys. All right, but it might work well for some of you that's kind of tired today. All right. So I think I'm just gonna stop my lectures today at this point and not touch on the Doppler effect yet. Okay, sounds like a good plan.
Okay.
And then next time we're going to jump right into this Doppler effect and the interference, and that will that will fit 2 hours lecture next time nicely. All right, that will be good. All right, guys, is that all right? It has to be. I have to go anyway. If you guys not, I mean, I still have to do it anyway. All right, guys, sorry for the sudden announcement. All right, but I thought I forgot to tell you earlier this lecture. All right, so any questions up to this point? Okay, so if not, then that is it for today's, guys.